through the future work section just yet.
Um, there are several opportunities for future improvement. This includes integrating real-time booking system, applying reinforcement learning for continuous optimization, supporting multimodal interaction, enabling group travel planning. Is I think this part is a kind of hard, and conducting large-scale user evaluation. This enhance would improve both functionality and practical applicability.
Okay, yeah, thank you, Sarah.
Thank you. Thank you for your time.
Okay, if we don't have any other questions, um, then we're gonna move on to Sukmani for her presentation, the last one for session number 2. So thank you, Sarah. Sukmani,
Thank
whenever you're
Thank
ready.
you.
Are we able to see the slides, Harrison?
Yes.
Okay, good afternoon. My name is Sukmani Thukral, and this is my capstone project, Epilepsy.ai, an agentic AI system designed to support community epilepsy awareness through automated RAG-powered email responses. My advisor is Dr. Sam Chung. So moving to the next slide. Here is a quick overview of what we'll cover today, starting with the problems we are solving, walking through the design and implementation, and then reviewing our evaluation results and where the project goes next. Um, Epilepsy affects over 50 million people worldwide, and 80% of those in low-income countries have no access to treatment. Beyond access, there is a communication problem. When people reach out to epilepsy organization for help, responses are delayed, inconsistent, or sometimes inaccurate. This leaves people with misconceptions at a time when they need reliable information. Our research question is, can an agentic AI system reduce those delays and improve the quality of responses? So, the motivation for this was there are two key gaps driving this project. First is a knowledge gap. Epilepsy education is severely lacking globally. Second, an architecture gap. Existing research does not address multi-agent systems for non-profit outreach specifically. Our solution combines agentic AI and RAG to generate customized domain-specific responses based on what the user actually asks. So for a background slide, legacy systems rely on generic resources, have no email integration, and depend entirely on human volunteers. Our project replaces that with a RAG-based pipeline running locally using Olama, a multi-agent design that allows edits at each stage, and a streamlit interface that keeps the human in control throughout. We reviewed 4 key papers. Kulako looked at agentic AI in clinical workflows. Zhang explored agentic AI for edge devices. Jang focused on information exchanged in medical systems. And Venkatesh Subramaniam applied agentic AI to personalized communication. However, none of these addressed a low cost effective automated response system for epilepsy awareness, specifically, which is the gap our project fills. So the matrix compares those 4 papers across 3 themes: agentic AI in healthcare, multi-agent architecture, and communication personalization. The rightmost column shows how our approach builds on each. We are the only one that combines all 3 into a local domain-specific email pipeline. 4 requirements drove the design: real-time processing for fast, accurate responses, a predictive approach to anticipate common query types, a multi-agent system with human in the loop to ensure quality, and a user-friendly streamlit interface so staff can approve, edit, or reject every response before it is sent. The pipeline has 4 stages. The reader agent summarizes the incoming email and classifies its intent into one of the 5 categories. The RAG module retrieves relevant epilepsy knowledge from our custom FES vector store. The responder agent drafts a professional reply using context, uh, and the reviewer agent polishes it for clarity and tone. At each stage, a human can approve, edit, or skip. We evaluate the whole system using BLEU, Rogue, and BERT scores. So this is our data flow diagram. The diagram shows full data flow. An email arrives via the Gmail API, gets parsed for content and intent, then passes to knowledge retrieval step. The system queries both the FAS vector store and epilepsy training data to pull relevant passages. The combined context feeds into the draft generation step, which uses the LLM to write a reply. Finally, the response goes to human review and approval before being sent to SendGrid. So this is a RAG pipeline in detail. Starting from the left, the agent extracts the core question from the email, converts it into a vector store embedding, then runs a similarity search against the local FAS index. The most relevant JSON knowledge chunks are selected. These include files like seizure first aid.json and seizure triggers.json. The context is inserted into a prompt template, which is then passed to the language model to generate a draft response. So the system architecture shows how everything connects at a higher level. The reader, responder, and reviewer agents all run on backend server alongside human in the loop logic. They communicate with Olama runtime locally via localhost API. Olama runs the V3 model for all 3 agents. The FAS index stores the epilepsy knowledge base, Gmail handles incoming email, and SendGrid sends outgoing replies. So we did some testing using Postman. Before running the full pipeline, we used Postman to verify that the Olama model was reachable and responding correctly. The screenshot shows a post request to the API chat endpoint. We sent a simple test message, "Hello, can you explain epilepsy in simple terms?" And the model returned a 200 OK with a coherent explanation. This confirmed that the chat format used by all 3 AutoGen agents was working as expected. You can see the response time was about 2 minutes and 24 seconds, which already pointed to the latency issue we need to address during optimization. So this is the second test used the API generate endpoint with a direct prompt, summarize seizure first aid in one paragraph. This server returned OK, 200 OK in about 45 seconds, which was significantly faster than the chat endpoint. The response included general first aid step, such as staying calm, cleaning the area, turning the person on the side, and calling emergency services. Um, if the seizure lasts over 5 minutes. This test confirmed that the Olama model endpoint was functioning correctly, but the detailed epilepsy specific domain knowledge used in the final system comes from the custom RAG database and not from the model itself. So this is our class diagram, and it maps out data objects and agent methods in the pipeline. Starting top left, an email object carries the raw input. It gets cleaned into a email, which the reader agent processes into a summary. That includes the email ID, text, and intent classification. The RAG retriever takes the summary and returns a context object with knowledge chunks. The responder agent uses both to generate a draft reply. The reviewer agent polishes it. The human agent then makes the final decision to approve or edit, and everything else persisted via the data store. So this is the full deployment diagram. This uses the user accesses the system through a browser running the Streamlit UI that connects over HTTPS to the web server which makes the API calls to the backend. The backend runs all three agents and the human in the loop logic using Python and AutoGen. It calls the Olama runtime locally for model inference, which performs a vector search against the FES, epilepsy knowledge base. Gmail brings in the incoming email, SendGrid sends the replies. The diagram shows Llama 3 for the reader and reviewer agents, which is from our earlier design, which was later changed to Phi 3. So this is our Streamlit interface, um, uh, showing a live run with a seizure first aid email. The 5 steps laid out are the reader agent summary for reading, RAG retrieves the context, sources CDC, Epilepsy Foundation. Then we have the responder draft reply, the reviewer agent, and then every text box is editable and the email is sent across once approved by the human agent. So these are pre-optimization results and for 5 email types that we used, and we are calculating blue Rogel scores, and we see that they are near zero, and which is expected since our main goal was to look for semantic similarity, which is what um, we see good results in. So, but what we see here is that out of 5, 3 cases failed, and this impacted our output. So we did another run. Yeah, I hear you, Harrison. Um, so we did another run, and here we were able to get all our 5 cases pass, and bird score remains strong again, and moving to the next slide, here we have visual evaluation metrics side by side, and we see that the bird score is high, um, consistently high, sitting between 0.84 and 0.88, and uh, and this is the primary metric for task and the results for stay. So here we are showing how we optimized our pipeline, and
What happened? I think she might have
She
exited.
disconnected, maybe.
I think she may have disconnected accidentally. Let me try and get her back in.
She's
Oh,
back.
there you are. Sukmani, can you continue?
Yeah, I something popped up on the screen, so I just it just got clicked. So yeah, so just give me a second and I'll upload the file so that we can continue.
Okay.
So I'll give a demo after this, but so I think we were on the results section. So agent performance, looking at agent performance directly, we see the that the post optimization performance was much better, as out of the 5 uh, cases um, were successful. So now here we have our error analysis. This breaks down exactly what went wrong in the missed meeting case. The reviewer timed out at 91 seconds because the input was too long. Fixing that, reducing input to 800 characters resolved it. The near blue scores are due to no n-gram overlap. And the low rogue L of 0.058 was because the review was bypassed and the draft was used instead. So, so we are missing factual in verification, and that is a layer that we need to add. And So that is something that is a limitation. And the test cases are only 5. So that is also very, there's a limitation. So we haven't done a lot of testing on this, but yeah. So here is a small demo. I have a recording. I can also do a demo after that. Uh, so So we start by loading the Epilepsy Awareness AI email assistant. So when I click over here, um, it basically loads the email and we see a summary here. And yeah, and then the RAG module kicks in. So we are able to get the sources of the data. And here's the draft, the responder agent. And then we have the final response, reviewer agent. And once that is done, we can send our email across. So I'll also share my screen and give a quick demo. But before that, the conclusion to summarize, we demonstrated a multi-agent RAG pipeline that can support epilepsy awareness and with a very high BERT score of 0.84. Future work would include multi-language support, a voice-based email response system that would help. Yeah, Harrison, I hear you. Okay, so I'll share my screen quickly. So, and see if I can. So I'll start presenting and I'll do.
Hey, Harrison.
Um,
Hi.
Oh, okay.
so, Sam, can you see my screen now?
Yes.
Yeah.
Now PowerPoint present screen. Yeah.
Yeah, so here is my code basically.
Uh-huh.
And so I'm going to be running the Streamlit app. Uh, Hopefully this should work, but I did give you a demo through the recording. What we are expecting here is that it would pull the email. So it will load the latest unread email from my Gmail account. And once the email has been loaded, it would create a summary from this. So this is a Streamlit UI, and I'm running Ulama, and we have a custom RAG database created. Um, so yeah, so this is the summary, and in the summary, what you see is that it is looking at the email. The sender is so it looked at the email that was sent, which was pulled from Gmail account. So here is my Gmail. So this was the email that it looked at. What should I do if someone has a seizure? So the email was pulled here by the system and it created a summary. So what the sender is inquiring about. So, and then and what the sender wants basically, seeking specific action to take during an immediately after an event. So what they're referring to here is as an event is epilepsy, and here, as we discussed, intent classification is our first aid question, so that it is a first aid question. The so so here we have our RAG module. So this is the source is CDC. This information has been pulled from CDC. Um, and then this information has been pulled from Epilepsy Foundation and so on. These are our sources from where the information has been pulled. And now, based on this knowledge base, we are generating a draft. So this is our draft that has been generated, which says thank you for reaching out with your inquiry. And so this is our draft, and this is our final. I can make changes to it. I can write something like, Dear Sam, thank you for your interest in understanding first aid measures, and I can send a reply. So, and the reply was sent successfully. Thank you. Are there any questions?
Thank you, Sukmani, for your presentation. Yeah.
Yeah.
Okay.
So if
Okay, Sukmani, would you go to the data analysis chart?
yeah,
Can you-
Sam, I
yeah, can
wanted
you-
to share this with you also, that here in SendGrid, here we see that the reply was sent across, and it has been
Yeah,
so this was
no,
the
no,
reply
no,
that was
not
sent
this one.
across.
Your presentation, go to the data analysis, there is a chart. I have a question for you.
Okay, so
Data analysis chart, yeah. I think you got a comment from me. That's why I'm curious. I didn't hear that. Data analysis chart, yeah.
I will share it. I'll stop sharing this and I'll share the PowerPoint. So data analysis. Okay, this.
No, next one. This is the
Okay.
data collect. Yeah, okay. Here, no. Go there, previous one. Previous one.
Okay.
Chart. There is the graph. Yeah, you said the bar graph.
Yeah, I have only one bar
Yeah,
graph.
sure. Yeah, stop here. Okay, so you said logger and BERT score, but where is the blue color?
Because that was 0, so it is not showing up here because the blue score was 0, and throughout, and it was very, very very low. So, and because the blue score is it's kind of it goes to the Lexia level. It does not look at semantic similarity and all those things. So those scores were very low. So for our situation, we were looking at semantic similarity, and BERT score was very high, and it met our requirement.
Okay, that's the why I did see the explanation in your report. That's why I brought my question. Okay, good. It's okay. I'm done.
Yeah.
I have one last question. So I noticed that you did mention that one of your runs kind of failed, or like it kind of stopped running halfway through, right?
Mhm.
Yeah. Since what kind of hardware are you running on your system? Because I know that if you are using a local model, because you're inferencing it through Olama, you kind of need like some decent hardware in order to process the model. So just curious.
Yeah, so basically Olama, we can have many models, right? Many different models. So we changed the model. So initially we had the system was failing, and that was pre-optimization, and the scores across the board were near 0 for blue, because we were not looking for word-to-word similarity. And as far as this is concerned, the failure is concerned, it ranged from the 5 cases were impacted by output quality. I mean, the we had to change it. We changed it to Phi3, right? We were initially using Llama. So Llama is not something that was working on my computer. It was it was taking a lot of memory and a lot of CPU power. So for optimizing that, to reduce the load on the CPU, we changed it to Phi3. And once we used Phi3, we were able to run the cases. There were other things also that were causing the system to fail, and that were causing um, the um, the reviewer agent to fail or the responder to fail, because we were not having trouble with our uh, uh, with loading the emails. We were at different stages, we had different issues, yeah, but yeah, mainly changing the model to v3 helped. So yeah, that was a model that uses less CPU power.
Yeah.
Harris, did it answer your question?
Yeah, I guess. I mean, because I kind of ran into similar issues when I was running my simulation. So I ran QWEN. First used the 9 billion parameter model, and um, I had some hardware that can pull it off, but still, it's still a little bit too big for what I had. I have a graphics card that can kind of accelerate the AI model. Um, but yeah, sometimes you kind of have to scale down the quantized model that you are using just so that you can get through the simulation.
Yeah,
But it's basically,
yeah, Olama has a lot of models that you can use. So
mm,
it's not just one model that you can use. There are many models, and there are a lot of models that you can, change across and test. So there's like Llama 3 8B that we tested, and there were other models too. So you have to basically uh, check which model is best for your use case, you know.
yeah, I agree. Okay, that should be it for my questions. If nobody else have a question for Sukmani, then we can conclude our applied research symposium today.
Thank you
Okay,
all.
yeah, thank you everybody for you know, I hope that this is gonna be a good start to the next chapter of your career, whatever you plan on doing after your graduation from City University of Seattle.
Thank you, Harrison. Thank you, Professor.
All right, bye everyone.
Bye.